Okay, so we have discussed about classification and object detection in detail now. And let's now move on to something like segmentation. So before moving there, let's quickly recap what is image classification and object detection looking for. So given an image like this where there is the presence of dog and cat, a typical classification looks like telling that okay, there is dog with probability 90% and cat with probability 90%. So that's what we are looking at, right? So you have the uh, probabilities for whatever number of classes that you're looking at, and then you're just saying the probability that you can find that particular class in that image is basically what classification is all about. We went one step ahead and we did the object detection, where we also not only classify the objects in the class or classes in that particular image, but we also localize where those objects are or where those classes are in the image. So we saw a lot of methods like single stage and two stage approaches, and essentially combining classification with localization is what we call as object detection. In this topic or today's kind of topics, we will discuss about segmentation. And segmentation is nothing but you take an input image and divide it into different segments. We can think of this as kind of classifying. So you're basically kind of trying to classify every pixel into one of the n classes. So basically in this case the classes is analogous to the segments. So you take the image, you identify that or you decide that you need to segment that image into n types. So we can think of that as n classes. So then the segmentation problem can be considered as a classification problem where you do for every pixel kind of a classifier which says that okay, this pixel belongs to one of these n segments. Okay, so that's the idea. So pictorially, this looks like this. So you take an RGB image like this, and uh, ideally or theoretically speaking, you expect something like this where you divide every pixel in the image into kind of segments. So you can say the background is separated, the plate in the image is separated, the grains are separated, the leaves are separated. So it's kind of a perfect scenario. Okay, so moving on, so how to approach it? Of course, image segmentation has been a classical image processing and classical computer vision problem for ages. There have been many handcrafted ways of doing the segmentation in literature. Highly encourage you to look into those, and we are not going to talk about them because our objective is to consider segmentation from a deep learning perspective. Okay, so in general, uh, the idea is you take an image and divide it into segments or regions, and how to do it? It can be based on similar visual characteristics. So when we say similar visual characteristics, that can be just based on intensity, or it can be based on intensity and color. So basically the RGB values, and it can we can add some more constraint like okay, maybe it should also consider the neighborhood of those pixels which are closer by a distance should also be grouped together in that sense. Okay, something like if pixels are of same intensity but you also look at whether they belong to a same distance region. Okay, so then you segment them, something like this. If you think of only intensity based, then maybe you can kind of segment this image into something like this. And if it is neighborhood based, maybe you can kind of go one step ahead and group pixels with same intensity which are closer together. So this is the kind of a rough idea. And in broad sense, we can divide segmentation into three types. First one is semantic, second one is instance, and third one is panoptic. So semantic segmentation is like I divide the image into segments, but the ability to distinguish intra object scenario, something like let's say several persons in the image, I only classify the image into person and background class. I won't classify this into like person 1 2 3 4 so on. So that intra object classification sense is not there. Instant segmentation means you not only segment into different objects, but you also have the ability to distinguish intra objects as well. So something like person 1 to 5 in this case. And in the panoptic case, it is the ideal scenario where you take the image, you segment it into all possible. So every pixel will be assigned a kind of an individual label, and that's really the best you can get in that sense. Okay, so theoretically, you can define something like semantic segmentation is you just classify pixel for objects, and there is no intra objects in that sense. Instance, as the name suggests, every instance of the object needs to be segmented. So this is something like you classify pixels for each instance of the object, and then the ideal scenario is like you classify for each pixel for each instance of the object. It means every pixel is not left like that. Okay, you just decide on every pixel in that sense. Okay, so we will have in this session we will have a deep dive into the semantic segmentation. Of course, we won't be covering all the deep learning models that came across, but few of them which are of extreme importance. A very crude idea, just like we did for the object detection case, is a sliding window plus CNN kind of approach, where you kind of slide a window throughout the image. You center the window at every pixel on the image, and for each window, you consider that image crop. For example, this is one crop which is the tree, the second crop which is on the face of the cow, and the third crop which is the grass image. So you basically take that crop and then you pass it through a CNN classifier and then classify that based on the number of segments you desire. For example, tree, cow, and grass. And for each of these center pixels which you are kind of cropping around, you assign that to a class, and later on each class will be given a color, and then finally you end up in getting something like this colored image where you kind of segmented each and every pixel of the image. It's good. It's actually a very good way to understand what segmentation is all about, but you can think of the complexity. So you have so many windows, and each window you need to pass it through a classifier. So if you have, let's say, n windows, you need to have n times the classifier running on it. And not only that, the other issues of the size of the window, and shall I do a striding of a window by 2 or 3, or one is good enough, all those things are going to be an issue. So it's a hugely complex, redundant approach, I would say. It's expensive and redundant. It's too simple way to kind of define this, and nobody uses this, of course, but it's just good to make us understand what is image segmentation all about. A slightly better approach, of course, it's not ideal again, but it's slightly better approach is to use a fully convolutional linear kind of arrangement. So you have multiple layers of convolution. Okay, and of course you can add a ReLU on top of it, but no max pooling at all. So it's basically kind of linear arrangement of convolutional layers, uh, and the final convolutional layer will have this size. So h cross w is the size of your input image, and the output image also, or output map, segmentation map, should also have the same size. And that's a very important problem, because if you think about image classification, you are kind of reducing the resolution of the image, and you really don't care about the resolution of the feature map at the last stage, because our objective is to identify the classes or predict the classes in the image. So you don't need to do that for every pixel. So your output dimension will be basically the dimension of your classes. What I'm talking about is something like this. So you may start with let's say C in cross H cross W, and then you pass it through a series of convolutional layers, CNNs, with you can say con 2D plus ReLU plus max pooling, right? So this is what you have, and this we have the fully connected layer, and it may have, let's say, 1 cross 1000 for a single image. So this 1000 is a number of classes. So you really don't care about the size of the image. It's not at all important. And similar is the case with object detection, where you add another thing here, which is the bounding box, right? So you have 1000 classes, so you have 1000 cross 4 or 5, which means the border or the values, xy values of the bounding box. So you really don't care about h cross w here, but that's not the case when we talk about segmentation, because for segmentation the output should have the same size, because we are going to create a prediction for each and every pixel, right? A classification for each and every pixel in this case. So this has to be the same as your input image. That's very important. And let's assume it's a color image, and you're starting with, let's say, three colors. You pass it through a series of convolutional layers, so no max pooling. That's very important to note, because I need to keep the resolution same, right? It has to be h cross w, but a set of linear convolutional layers, in that sense, linear in the sense like no resolution change. And then finally, the channel number in the final convolutional layer has to match with your classes. So if you have C classes, this has to be C channels here. So C cross H cross W. And then once you do this, it's very important to create a single map. You just take the argument max in this direction. So you, for each pixel, you consider, so if I take one pixel, it will be like C cross 1, right? This is 1, so 1 cross 1, maybe I'll collapse it. So this is for one pixel, 1 cross 1 is one pixel. So for each pixel you have C prediction, C probabilities. You take the maximum, which index corresponds to maximum, so that will be the class for that pixel. So we already define a color for that class, and then of course you kind of map it, you will get the segmentation map like this. So very easy. So you take arg max, which is nothing but the index corresponding to the maximum probability value in the C direction, the channel direction, and basically that will be a class for that pixel, and you assign a color to it, you get this. So that's the idea. Okay, so very trivial approach, but very interesting in that sense. Like, this makes you understand how should you define or design a convolutional neural network for a segmentation task. But the problems here, you are not really reducing the resolution, so that means the receptive field is kind of very linear. Okay, so you, if you, let's say this is 3 cross 3 kernel you're using here, there's another 3 cross 3 kernel, so effectively this will combine and give you something like a 5 cross 5 receptive field. So if you want to look at a full image, you need to have a deeper number of layers, or a deeper convolutional neural network in this case, and that's not really ideal in that sense, right? But more important is, you're not reducing the resolution, so that means the convolution may be operating on the same kind of receptive field, which means a lot of information is redundant and it's expensive because you need to go deep here. So this is not really ideal, but again a very good way to kind of understand what is or how to define a convolutional network, or how to design a convolutional network architecture for image segmentation problem. Okay, so having defined or shown very trivial crude approaches which are not practically useful, let's bring up the very first kind of convolution neural network based segmentation approach, which was proposed in 2015. And the idea is something like this. So this part, let's concentrate on this part for the moment. So this part is very well known to you. This is a classifier kind of part. This we call typically in the neural network world as encoder. So you're basically encoding the input image to features here. So the idea is very simple. You have convolutional layers followed by activation layers plus pooling. So you kind of reduce the resolution. So you can say this is H cross W. So maybe at this stage, probably at this convolutional stage, it may be H by some number cross W by that number, right? So the resolution or the size of the image is kind of reduced, and then you flatten it, like 1000 is like a fully connected, so it may be 1 cross 1000, which is like the fully connected layer here. So this is, you bring down the resolution, and then we can safely say that this guy nicely kind of embed your image into a low resolution feature space. But of course this is a higher dimensional because you have 1000 dimensions here compared to, let's say, 3 cross H cross W. So this is the resolution, this is the dimension. This is a 3-dimensional image which is getting converted to something like a 1000-dimensional vector, and that is a high dimensional space, but the resolution is poor. So that's very important to know. Okay, so but this we cannot use in the case of segmentation, because this is we know that we need to predict for each and every pixel. So the resolution has to be back to H cross W and not like 1 here. So 1 cross 1000, if I take, it should not be 1, it has to be having the same size as H cross W, or an ideal case this has to be 1000 channels H cross W, right? That's the objective here if I have 1000 classes. Okay, and for that, what they actually proposed is a reversal of this process. So what this does, the encoder does, is it takes the input image of a high resolution, it brings down the resolution. Of course it increases the number of dimensions. This has to do the reverse. So it has to reduce the number of dimensions. The number of dimensions should be the number of classes whatever you desire for, or the number of segments in this case what we desire for, and the resolution has to be same as your image resolution. And for that part they call it as decoder, and we need to kind of reverse this downsampling. That's what we do here, right? So you downsample the size of the image, so you need to do the reversal of that, which we call as upsampling, right? So that's what exactly they propose, but they proposed it in a classical way. So I'll explain what exactly I mean by classical way. It is something like this. So you have the image, you have pool 1, you reduce the resolution, pool 2, you reduce the resolution, pool 3, okay, so you reduced it to like a very low resolution which is here, and then of course you flatten it. So what they're saying is like you just need to upsample it back. So you need to upsample this back to the finally to the full resolution as your original image. So how do you achieve that is you go and upsample it 2 times because you did 2 times reduction here. So this has to be 2 times upsampling here, and then you take that kind of thing and kind of add your previous thing to the upsample version, and you later on upsample it like 16 times to come up with the final. So but this upsampling, whatever we are talking about, the increase in resolution from a, let's say 1 cross 1 to 2 cross 2 to 4 cross 4, this upsampling is done in a classical way. It's not really done with any learned way or any neural network in that sense. Okay, but having said that, let me generalize now, and then we will discuss about various ways to upsample. So there are 3 ways we could put. So one is, I think we discussed all this now, so I'm not going to repeat that. The 3 ways is basically, one is the classical interpolation, that's what proposed in this paper. Then there is another method which is proposed known as unpooling, and the third method which is known as transposed convolution or deconvolution, which is popular or maybe the best approach which is used in all the contemporary architectures which are used for segmentation. So few things, few takeaways from this slide. The idea is you need to have encoder, which is the classical side which we discussed a lot, but we need to have a decoder which kind of reverses this. So if encoder is all about convolution followed by ReLU followed by downsampling using max pooling, the decoder part is all about upsampling. And there are 3 ways to do the upsampling. One is the classical interpolation, which is proposed first. There is no learning in this part, so that is the important aspect. There is no learning at all. The back propagation happens only in this part, in this particular paper. And then another way to do is unpooling, where there is learning introduced, so we'll discuss about that. And then the most common or the state of the art is kind of using the transposed convolution approach. So we'll explain what is this classical interpolation in a moment, and then we will go to the other 2 approaches to wrap up the discussion on the semantic segmentation side. Okay, so the classical way, the very simple or the crude way is something known as nearest neighborhood. So let's say I have a 2 cross 2 and I need to increase the size, the resolution to 4 cross 4. So I have 4 pixels here. So you kind of start with 10, 20, 30, 40. So the nearest neighborhood, anyway, the slide will explain it, but let me do through handwriting here. So the first step is you put these pixels to the borders. You blob up to this, and to start with, all others will be unknown. So you don't know what to put. The nearest neighborhood, as the name suggests, is you, let's say this pixel is what I am trying to fill in. You see the nearest neighborhood. So there's a value here, there is no value here. So I take the value of the nearest neighborhood. And similarly 20, I'll take this. So this will all be assigned with, so this is the kind of pivots, right? So you only have the pivots and non-values. So you go with the nearest, so the nearest non-value. So you have these, and this of course will be 20, and this will be 30, and this will be 40. So this is as simple as that. Okay, so that's the nearest neighborhood. So it's like if you want to show it in a plot sense, so if you are here, you will take this value. If you are here, you take this value. And 2D sense, you can think of this way. You do it in one dimension and then you do it in the other dimension, just like we did it over here. Okay, so that's the idea. So idea is you blob up and then you kind of fill the pixels based on the nearest neighborhood. Very trivial approach, but you can already see that this is going to be like really pixelated, because this look like a black and this look like a brighter spot compared to this. It's like pixelated way of looking at it. So it's not used, but it's very simple and maybe the fastest way of doing upsampling. Okay, the most common is something known as bilinear interpolation, and this is also not very difficult to understand. So again, the idea is you kind of blob up to the edges, and now is the most important part. So you can think of these as locations in space. So let me put the values in suffix here. So 0th location, and you can say 0 0 in that sense, 0th row, 0th column. And this one, if I put the second dimension as the column, so you can think of 6 0 comma 1, because it's still the 0th row, right? So this will be 0 comma 2. I'm talking about this location. Okay, and this will be 0 comma 3. And similarly in this direction, this guy is 0 0, that's already there. The next one is 1 comma 0 because this 0th column but first row. So this is this guy. This is 2 comma 0 and this is 3 comma 0. So randomly if I take this one, this is basically the third. So 3 comma 1. Okay, so that's the idea, right? So sorry, 2 comma, because we are starting at 0, right? So 2 comma 1. The first one is 0. So this 0 1 2, right? So this is 2 comma 1. Now what we need to actually do is, the name suggests it's kind of linear interpolation, and by, because you are doing it in one dimension and then you do it in the next dimension. So two linear interpolations you can think of. So how to go about this is basically you kind of find the slope between this. Okay, once we have the slope assuming zero intercept in that sense, then you can kind of predict it using this particular expression, right? Y mx plus c, right? So m is the slope, x value is where I want to find the corresponding y value, and c is assumed to be 0 at this point, so it will be y into mx. So first step is find the slope. So slope is basically, you can think of, uh, it's a derivative. So slope is basically the y value. Y values are these values you can think of. So and divided by, so x in this case, so when you consider this direction, you only need to consider the x direction, or the changing direction, rather the y direction in this case. And when we consider this, we consider the changing direction. Maybe I'm complicating it, but let me explain it this way. The slope here is 20 minus 10, that's the value, divided by the corresponding varying value, which is 3 minus 0, right? So this will be 10 divided by 3, which will be like 3.333 infinite times. So that means the slope is 3.33. So now if I want to find this value, you just need to basically consider this value plus this, whatever change in slope. So this will be like 13.33 in that sense. Okay, so let me explain it using this this particular guy. So let's say this is x1 y1 location, this particular value, and x2 y2 location. So in that sense, this is x1, this is x2, and if I plot the y values here, so this is y1 and this is y2, and let's say this is xy, some unknown value x, so non-value x, which I need to find the corresponding y. So that is a problem that we are addressing here. So let's consider this case here. So what is the slope for these two guys, or maybe with respect to xy and x2 minus y2? So this will be like, I'll put this way. So y2, or maybe I should not uh, do complication here. Okay, so interesting. Okay, so consider this expression. So if I put it to this side, okay, so you just take y2 minus y1 by x2 minus x1 at one stage, you just put this way. So this will be y minus y1, and this will come to the denominator. So x minus x1 is equal to y2 minus y1 by x2 minus x1. So this is the slope and this is the slope. So this is the slope between, you can say, I think, sorry, this is x1 comma y1, this is x2 comma y2, and this is x comma y. So the slope between these two guys is given by this, and these two guys is, or these two guys is given by this, right? They have to be same, because if you are fitting a line here, the slope cannot change. And you rearrange this, you get this expression. So if you put y on the left hand side, everything onto the right hand side, you get this expression. And this is the expression what I used in this particular case. So y2 minus y1 by x2 minus x1. So y2 minus y1 is 20 minus 10, that is 10, divided by, we saw it 0, 1, 2, 3. So 3 minus 0, so that is 3.33. So this guy over here is basically 3.33 whatever. And then this one is, so y, basically you want to find this value. This will be this value, which is this one, plus x minus x1. So that is 1 minus 0. So this will be 1 into 3.3. So 10 plus 1 into 3.33. That is the value coming here. And this one will be 10 plus, this is 0, 1, 2, right? So 2 minus 0 is 2. So 2 into 3.33. This will not change, right? So it will be 16.7. So that is here. So similarly, you can do it for the below side also. So this is what we call as linear interpolation in both dimensions, or simply bilinear interpolation. And you can actually go higher. You can put a cubic, so quadratic kind of fitting here instead of linear fitting, and that's also possible. So you have bicubic interpolation, or you can fit a spline also, that's what we call a spline interpolation, and so on. So this is a very simple approach, but it's very widely used to kind of. So don't lose the big picture. What we are doing is, because this guy I want to increase the size to 2 cross 2 to 4 cross 4 for the decoder part, and this is how they do it. So you have a feature map like this, you do the linear interpolation like this, you get the new upsampled feature map. Okay, so that's the idea. Now you can upsample it to 8 cross 8 in a similar way. Okay, so that's the idea. Okay, and the problem with this approach, or let me go back to the initial slide. So problem with this approach is this part, this particular guy, there is only classical bilinear interpolation. So everything is kind of done using bilinear interpolation and no learning. So no propagation. So no learning here. Absolutely no learning. Only the back propagation happens in this case. Okay, and then the next approach, of course, is like, let's have, so this is the same network as we have seen in the previous. The only difference is actually they are using a technique known as unpooling plus convolution in the decoder part. So this is a typical encoder which we already know it. This is basically the decoder. So you have everything, you have the bottleneck layer here, and from that you increase the resolution back. So you see the resolution 2 cross 2, sorry, 224 cross 224, and here also it's 224 cross 224. So that's the idea. So how does they achieve this is a small trick in these max pooling. They kind of propagate the max pooling indices to the respective stages where you need to upsample it back. Like for example, let me go slow here, erase all the unnecessary things. So you have 7 cross 7 here and 7 cross 7 here, and you had come this 7 cross 7 from 14 cross 14, right? So there is a downsampling here, and here there is an upsampling. So for this they introduce a technique known as unpooling, and unpooling is an interesting approach where you kind of store the indices from which this max pooling guy took the values to reduce 14 cross 14 to 7 cross 7. So I'll explain that in this slide. So let's say this is a 4 cross 4 case at some stage of your encoder architecture, and you use the max pooling to bring it down to 2 cross 2. So you basically have this patch and you take the max value, which is this. You take this patch, you take the max value this. You take this patch, you take the max value this, and you take this patch, you take the max value this. And that is how you arranged at 5, 6, 7, 8. You arrived at this. This is a classical way of doing it. So in this proposed network, what they also did is they remembered the position which had the max, which is shaded in different colors here. So this index, this index, this index, and this index is kind of stored for later use. That's very important. That is passed on to the unpooling or the upsampling stage. So let's say this is a lot of layers happening here, maybe a bottleneck layer, and then you come back to some value 1, 2, 3, 4. Some after some processing you got these values. Now this is 2 cross 2. I need to upsample it to 4 cross 4. Okay, so now how they do is actually this process of max unpooling is something like this. You know the indices, so you know these are the indices where you need to put the values in. So it's initialized with all zeros, and then whatever indices which is kind of passed on from this guy were stored and then you reused here. So these are the places where you pop up these 1, 2, 3, 4 values. So 1 goes to here, 2 goes to here, 3 goes to here, and 4 goes to here. Everything else is 0. So that's the idea. So you have the stored location which is being reused when you do this process known as max unpooling. So you kind of reversing by indices in that sense. So this, of course, then you need to 8 cross 8, you need the previous 8 cross 8, those indices should pass on to here, and then you do the same process here. The key thing is the next operation. So you have the max pooling. So let me put this unpooling operation putting here, which is this guy. This will be followed by a convolution 2D. So that's the idea. Okay, so this convolution 2D is going to learn as well. Okay, so I think I'll go back to this previous slide here. So this unpooling is there, and then you have the convolutional layers. So these layers will get trained or learned or backpropagation or gradient weighted during the backpropagation stage, unlike the previous case where the entire upsampling was kind of classical way of doing it. There was no learning layers here. So that's the key things they have introduced uh, in this particular work. So I'll reiterate it. So the downsampling, upsampling has some kind of index mapping, which is very important. The second is this unpooling will always be followed by a convolution which is learned. So that's two key critical things which are introduced in this particular network, which is proposed slightly later. But this is where the learning was kind of introduced into the decoder part. Okay, so this is important, but the problem here is it's not a very trivial way of doing it, right? So the next work kind of makes it more kind of meaningful or makes sense to kind of apply. There is a logic to it. So that's what we call SegNet. It's kind of very regular. So I kind of mimic SegNet with VGG, where kind of regularity was introduced into the segmentation task. So this part again, by now you are very well aware. So you take the image, you kind of reduce the resolution in the image, and this one you kind of reverse that process back. Okay, so that's a very critical stage, and there is skip connections also kind of introduced in this particular case. And in fact they also used the max unpooling approach here, but the I mean to start with, but then they realized that they can achieve the same thing using this thing known as a transposed convolution. So we will use that. We will explain that in a moment. Okay, so let me explain the upsampling part very clearly here. So assume that it's a 3x3 convolution kernel that we are going to use with the stride of 2, and you have an input of size 2x2 and output of size 4x5. So the kernel that I'm going to use is 3x3. Okay, so 3x3 kernel with the stride 2. So what I'm going to do is, the first step is you kind of take this 2x2. So this pixel, I'll kind of multiply this particular pixel with each of these values. So I have 3x3 values there, and then I put that 3x3 values like this. Okay, so you kind of weight this pixel with this kernel. This kernel of course is the kernel which will be learned, and that you kind of put it here, whatever values. So same values will be kind of coming repeating and putting. So whatever this multiplied by this, and then you put it over here. Then you take this guy, so that will be multiplied with the same kernel, and then you kind of put. So but there's a slide of 2, so the sender will go from here to here. Okay, so slide of 2, and then same values will be popping up here, but then there is an overlap. So this region is kind of overlapping region. So there what you do is this, you sum up. So values will be getting summed up in these overlapping regions. You repeat this. So next one is this guy. So you have the kernel sender. So you see stride of 2 again. So you have this here, and similarly this one. So you have this. So wherever there is overlap, so those regions kind of get summed up. Okay, so that's the idea. So I think this is also overlap, kind of, right, symmetric. So these regions are summed up. The remaining regions you have some unique values, and then of course the size is now slightly higher, but you only need an output size of 4x4. So you kind of trim those regions out. So let me remove it thing, and you have the 4x4 region, or wherever there is overlap. I only shown this region, but wherever there is overlap it will get summed. Okay, so that's the idea. Okay, so this is what popularly known as transposed convolution, which is already a command in PyTorch, for example, and it's a very logical way of doing it compared to something like an unpooling or the classical interpolation. Okay, and fast forward actually. So this is something which is a very popular segmentation network. So we talked about classical interpolation, unpooling, and then transposed convolution. So UNet is an architecture which kind of reuses the transposed convolution, and but they added something known as the residual connections, which was getting popular during that time. We already know this, but there are few differences which I'll explain. But why it is UNet? Because it takes the shape of U, but you can actually think that any segmentation network will have to take this shape. Okay, so you have the encoder here and you have the decoder here. So it's a concept we already learned a lot. So two things happening here. So one is basically all the benefits of encoder decoder approach which we considered so far, but with residual connection. And the residual connection, there is a slight difference here. So typical residual connection, if you remember the ResNet architecture, you remember there is these layers coming up, and then you have a skip connection, but you have a summing operation which is happening. So this was kind of summing. But in this case, if you see, this layer is kind of appended with the layer which is coming here. So concatenated here. It's not and not. So not summed. This is very important. Okay, so that's a very important difference. So you're kind of concatenating the features, the previous features and the upsampled features together. And of course, all these layers are learnable, just like the previous SegNet architecture. So this has been a very popular architecture unit in medical imaging to start with. And nowadays, if you think, the diffusion models even use UNet as their base architecture. Remember, the diffusion models are kind of generative neural networks. So we'll generate images. So they have to be high resolution, just like segmentation task, but they are kind of using the UNet architecture as their base. So it's not just used in segmentation, but also in diffusion models as well. So that's the very reasonable importance of UNet. And fast forward, the state of the art till the intervention of the vision transformers was this DeepLab and its version. So I'm just briefly explaining the version 3 of DeepLab here. Uh, and key concepts, of course, we handpicked each of these segmentation neural networks so that we know there are certain interesting aspects introduced along the way. So this is one such case where the these guys are from the Google team. So they introduced two concepts, I would say, or rather one concept which is a combination of two things. One is this concept known as Atrous convolution, or we call it as dilation. Okay, it's popularly known as dilation. And then separable convolutions. Okay, separable in the sense like depth separable, which is using these one cos one operation. Okay, so the address convolution is basically will increase the receptive field, and I will have a detailed explanation in the next slide. So we'll go there and we'll explain what is address and what is separable in that sense. Okay, so the other things are all same, encoder decoder kind of architecture and upsampling and all those things which is we already introduced. The major difference is like instead of the standard convolution, they're using these address convolutions as well with a different rate, and that's something which makes it unique in that sense. I don't think they're doing anything on the decoder side, but it is more on the encoder side, and this is kind of motivated. So this Atrous convolution is motivated by the exception architecture and the mobile net architecture. I will say why. Exception is, or rather, this was the Atrous was proposed in exception, which inherently was motivated from the inception architecture. So inception, we know that we are looking at the same input by different convolution kernels, right? So that's the idea which is inspired from inception. But instead of having like 1 cross 1, 3 cross 3, 5 cross 5 kernels manually, what they're doing is they're using the same 3 cross 3 but increasing dilation rate. So we'll know what is dilation in the next slide, but it is something like you're expanding the size of the kernel through this operation. That's why we call as Atrous convolutions. And this is actually kind of done in a single stage. That's why it's inspired from inception in that sense. It's like an inception module. And then depth convolution was used, or group convolution, depth convolution, what they call, is used to come up with reduction in the complexity, which I'll explain in the subsequent slides. Okay, so the address separable convolution is something like this. So you have a convolution layer, let's say 3 cross 3, and this has a rate of 1, which is nothing but a simple 3 cross 3 kernel. But then if you have a rate of 6, it means actually you have a 0 between every kind of 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5. So basically like almost expanded the kernel size to like 5 cross 5 by filling 0. So that is the idea. And 24, if you have a 24 rate, it's going to have a very high, I mean, you can think of the receptive field is also increased in that sense, right? So this is the generic idea of dilation. And if you do this, the simple concept is all others are filled with zeros, and this will effectively kind of reduce the receptive field of your convolution. Okay, the other way to of course do is max pooling or increase the number of convolutional layers, right? So instead of that we can do something like this. And then yeah, the standard convolution expression, except that these are zero, so you don't need to operate the remaining multiplications, only the relevant multiplications you need to kind of use. The depthwise convolution or the separable convolution is also important, where the idea is like when you do the convolution with the input channel, you don't do that um, as a batch. So for example, if you have something like 3 cross H cross W, 3 is the color channels, and when you apply it, you may want to do it 3 together, right? So that's not the case you're doing. You take the channels, the desired number of output channels separately, and then multiply each one of them separately. The channels are also kind of, you can see here, there are 3 convolutional kernels which are getting multiplied individually. And then we already know about the point wise convolution, where you can increase the number of channels to whatever number you want. And that Atrous depthwise convolution is like you have the same advantage of depthwise convolution, but you have Atrous convolution. So you can say the zero padding, or see the zero padding here. So you combine the Atrous convolution with the depthwise convolution. That's what used in uh, the DeepLab version 3 in that sense. Okay, and moving forward, the advantage of the separable convolution. So we talked about the importance of Atrous convolution here and Atrous separable convolution here. And the simple reason why Atrous convolution is useful is like you can have wider receptive field compared to a simple convolution. But depthwise convolution has slightly more advantages. So let's explain this using a case where it's not done and case where the same thing can be done using a depthwise separable convolution. So let's say I have a 5 cross 5 kernel and I need to kind of apply it on 3 input channels, and the desired output channel is 256. So total multiplication involved is the output kernel size will be like 12 minus 5 plus 7 as minus 1 plus, or 12 minus 5 is 7 plus 1, it's 8. So 8 cross 8, which is assuming zero padding, as no padding and stride of 1. You remember the formula, width minus the kernel size plus 2 times the padding by stride plus 1, right? So this is the operation. So you put p equal to 0, s equal to 1, and k equal to 5, and w is equal to 12, you get 8 cross 8, right? So that's the place where you get the number of output pixels. Now the operation here is you need to do it for all the output pixels, so that is there. And you have 256 output channels, that is also there. You have 3 input channels, that's also there. And you have 5 cross 5 kernel. So 5 cross 5 kernel has to go around all the 8 cross 8 locations, and it has to go 256 times to create the 256 channels, and of course 3 input channels we need to. So this is the total number of multiplications it is expected. Now, if you do this in 2 steps, okay, so first step is basically the separable convolution. So that's what we do. So we do this in 3 kind of channels separately, and then you stack them together, and then you run a 256 channel 1 cross 1 convolution. You end up in getting the same size. So these two are equivalent, but the steps to achieve this is kind of divided here. So now let's see the total multiplications if you do in these 2 steps. So this step, if you see, it has 8 cross 8 locations again, definitely, and 5 cross 5 kernel and 3 input channels, but only 1 output channel per time, right? So that's the critical case. So 1 2 3 are stacking them together, so only one at a time you're doing it. So that's this one. So that is this operation. And then this guy, you have again 8 cross 8, so that is definitely there. And then this has 256 output channels, and then you have 8 cross 8, 3 channels to do, because now you are operating it together. So you have this total operation. So you compare this and this, so you can see so much reduction in the number of multiplications in a very sense, right? So that is something which is very interesting actually. So that's one of the kind of idea that is being leveraged in this DeepLab version 3. So this is just a recap here, the advantages of doing the separable convolution, and this is what being used in mobile net to reduce on the complexity. Okay, so this operation, I think we didn't discuss that in detail earlier. Okay, so this is how you implement the Atrous separable convolution in PyTorch if you want to do it. So you define the depthwise convolution as this. So you have basically the dilation value you need to put. So you can actually fix it as 2 to start with, but of course you can change it in that sense. And you kind of do it channel wise. So you group in channels. So whatever the channels, you kind of group them together and do it parallelly. So it won't be done across all the channels together in that sense. And then point wise convolution, you already know it. So this is a second stage, right? So first you do the depthwise convolution in a dilated manner. That's the Atrous convolution in a depthwise separable manner, and then you do the pointwise convolution to bring it to the same dimension. Basically, these two steps. So this is first step. This is second step. Is shown here. Okay, so that completes the semantic segmentation part.